Okay, welcome back. And now what we're going to do is we're going to start by exploring some of the properties that we've seen, or see if we can find out what the properties are. Okay, and try to figure out why these formulas work or why they are what they are. We're going to do some exploration into understanding some of this. Okay, so one of the things is, if you notice for the 1 by 1 case, it says A is non-singular if and only if A is not equal to 0. And then of course we've seen this one too for the 2 by 2 matrix is non-singular if and only if this difference is equal to 0. And then of course if we do the 3 by 3 case, we have this family formula is non-singular if and only if this is not equal to 0. So when we first look at this, there's obviously not an obvious pattern to what we're looking at. At least I don't see one. Well, what else can we say? Well, if we look at this, what are some of the things we might notice, right? Notice that there's one letter here in the 1 by 1 case. In the 2 by 2 case, we see that each of the two terms has 2 letters in it. And in the 3 by 3 case, we see that, now in this case here, there's 6 terms, but each of the terms has 3 letters in it. So maybe that's something. Now, it might not, well, even those things that we notice may not do us any good as far as making it make more sense. It probably makes it more puzzling than anything. Another question is why are they being subtracted? Why are some of them added and some of them subtracted? Okay, that's another question. Where does that come from? Now, if you look at it, you might even notice that, like for example, like in this case, it's trivial. But in this case, notice that in this term, A and D come from different columns. So does B and C. Okay, here you might notice the same thing, right? Take each term, A, E, I. A, E, I is in different columns. Or if you take C, D, H, right? You've got C over here in this column, H, and D. Right? So there's something you might notice. And you can confirm that in the same case, right? But again, does that really help us? Not really, at least not to me it does. But here's the thing. A good strategy for solving problems is to explore what properties the solution must have. And then to search for something with those properties. So what we'll do is we'll start by asking what properties we'd like the determinant formulas to have. Obviously, we know that they can't be 0. Okay? And at this point, our main way to decide whether a matrix is singular singular or not is to do the Gaussian reduction, right? That's what we do. And then check, once we do the Gaussian reduction, check to make sure we don't have any zeros in the diagonal. Okay, in other words, when we do our Gaussian reduction, we should be able to take the product of the diagonal entries, and that should not be 0. So maybe that is something that we can maybe look into. So we would guess that whatever determinant formula we find, the proof that it is the right, may involve applying Gauss's method to the matrix to show that in the end the product down the diagonal is 0 if and only if the formula, or excuse me, let me say it this way. The product down the diagonal is 0 if and only if the formula is 0. So this will suggest a plan. So what we'll do is we'll look for a family of determinant formulas that are unaffected by row operations and such that the determinant of an echelon form matrix is the product of its diagonal matrices. Okay? Now what we're going to do is we're going to test this against 2 by 2 and 3 by 2 formulas, and in the end we'll have to modify our comment about being unaffected by row operations and go from there. So let's start with the 2 by 2 and 3 by 3 cases. Let's look at those and go from there. We'll do some row operations on the general 2 by 2 and 3 by 3, and we'll see where that takes us.